In problem 145, we have this bar which is hanging from point O, and it is in stationary condition, and we have this piece of clay which is moving in the horizontal direction with velocity of v1. And let's say it is very close to this, and let's say there is no gravity. And this piece of clay, after the impact, is going to stick to this bar. Then everything is going to rotate about point O. And the question is, what's going to be the angular velocity of this bar plus this clay all together immediately after that impact? I would say think about this problem for 10 minutes before seeing the rest of the video. So during the impact, if you consider these two together as your system, then during the impact force between these two is going to be internal force. So we don't need to consider that force. But we are going to have some reaction forces at O. Because we have impact here, those reaction forces could be really high. But if you think about it carefully, you're going to see the moment of all of these forces about point O during the impact from 1 to 2. 1 means before impact and 2 means after impact. After impact. From 1 to 2, sum of the moments of all the forces that we have on this system, which means this bar and this clay together, about point O is equal to 0. Because the only forces that we have, the only external forces that we have are going to be these big reaction forces at point O. And even if you have gravitational force, the gravitational force is going to be comparatively very small compared to those impact forces. Even if we say that gravitational force is not really small, the moment of it about point O is going to be equal to 0, because the gravitational force for both of them are going to pass through O during the impact. So we can say some of the moments about point O is going to be equal to 0. Because some of the moments about this point, which is on this body, is equal to 0, we are going to have HO2 is equal to HO1. The angular momentum before impact, angular momentum after impact. So the only thing we need to do here is calculating the angular momentum before and after impact. Okay. So HO1, H of the bar is 0, because H of the bar about point O is I times omega, and omega before impact is equal to 0. So H for the bar is 0. H for this particle is going to be rho cross mv, and let's say this particle is very close here. So rho of it is going to be L divided by 3 downward. And if you cross product it to m times v1, the cross product is going to be in negative z direction, right? This is negative j, and this is negative I. J cross I is going to be negative k. So it's going to be negative m L divided by 3 times v1 in the z direction. And after impact, everything is going to rotate in clockwise, and the total angular momentum is going to be IO of the whole system times omega, but omega, because it's going to be in clockwise direction, in the z direction is going to be negative. And IO is, for the bar, is going to be 1 over 12 mass times L squared plus m times the distance squared, right? So the centroid of the bar, let's say it is here, mass moment of inertia for the bar by the centroid of it is 1 divided by 12 mass times L squared. Using parallel axis theorem, we need to multiply mass to the distance squared, which is L divided by 6. And the mass moment of inertia of this particle about point O is going to be mass times the distance squared. So we need to add small m times L divided by 3 squared times omega. Put these two equal to each other, then from there we can find omega, right? So HO1 is equal to HO2. From there, omega is going to be equal to, after simplification, it's going to be 3 times m times v1 divided by small m plus capital M times L. And the direction is going to be in clockwise.